So this example is in honor of our host, Nika Alongo, who isn't here, but might show up. Taking a look at data from the second generation Johns Hopkins University Preventive Intervention Research Center trial and focusing on the aggressive disruptive behavior items we have talked about a little bit before. It's teacher-rated items. Here you have them in a more complete listing than we talked about before. You have your favorite stubborn item up here, breaking rules, harming others, etc., down to loses temper. And this is a variable that is scored from 1 through 6, almost never, rarely, sometimes, often, very often, almost always. And one question is how to analyze data like this. What kind of outcome scale type should you consider this to be, and what kind of model should you have for this? We are interested in trying to find underlying dimensions for these items, and we really want to see if this measurement instrument is unidimensional or is perhaps multidimensional. We care about that because we suspect that maybe if there are different dimensions, those different dimensions could function differently with respect to an intervention like this. And we want to be careful to use sums or average of these items if the unidimensionality does not hold. We have 362 males in 27 classrooms in this case. So we have students nested within classrooms. It's barely meeting Linda's minimum cluster requirement, minimum number of cluster requirement. But 27 should work fine, both for type equals complex or type equals 2 level. And I'm just going to talk through this example a little bit today. I'm going to show a little bit, some more analysis of it tomorrow. The hypothesized aggressiveness factors that one could conceive of as being underlying here are verbal aggression items like yelling at others, talking back to adults, losing temper, and expressing stubbornness. So seeing that as verbal forms of aggression, one also could say from face value of these items that maybe there are items geared towards property aggression, breaking things, harming property, taking others' property. And perhaps person aggression, fighting with classmates. So maybe there are a couple of dimensions underlying here. But returning for a second to the scale, you have a situation where very often you would treat this scale as continuous, scoring it from 1 through 6 and just go on with continuous variable technology, standard factor analysis, be it exploratory factor analysis or confirmatory factor analysis. But there is one complicating feature here, and that is that we seem to have a floor effect. In almost never category, you have quite a high percentage of individuals, up to 73% here, where for these children, the teacher didn't see any evidence of any of these aggressive behaviors, and then tapering off out to the tail. And we've been analyzing these data in quite a number of different ways in this prevention science methodology group. We've tried to take into account the non-normality by using censored normal techniques, by using two-part modeling, by ignoring it, and by treating the variable as ordered categorical, And again, an ordered categorical variable has no problem. An ordered categorical methodology or model has no problem taking into account piling up here. That's not a violation of any assumptions of the ordered categorical model. It would only be a problem if you treat this as a continuous variable. It certainly will be a situation where continuous variable methodology that tries to apply non-normality robust techniques for standard errors and chi-square would not be sufficient, because you have this large degree of piling up on the item level. You do a little bit better if you take the average, then you get rid of some of the piling up at the lowest point. So we're actually going to talk about this tomorrow in terms of ordered categorical factor analysis, but two-level ordered categorical factor analysis. And that's seldom done in the case of having potentially this many dimensions. It's interesting to think about these dimensions. If you do our standard diagram of the modeling, you can portray it this way. You have a within and between classroom variation picture. You have the 13 items up here, and you have 3 factors potentially that you could look for. They are the factors that you saw in the previous slide. Now you could then, on the between level, oh, it's still sleepy in the afternoon. I tried to restart it, but it's okay. So you can have these 3 factors. These make sense on the in terms of variation across children. But what about the between level? Well, first of all, we do the random intercept approach here with filled circles at the items, and they become open circles on the between level, continuous latent variables in the shape of random intercepts. And we could hypothesize that there are 3 factors on the between level as well. But you have to think about what that would mean. You know, individual level variation is one thing, but across classroom variation is another. Do you really think that you have 3 different factors on the classroom level? That would say that classrooms differ with respect to all of these 3 types of aggressive behavior. You can think of these, one way to think about this, that these variables sitting here, think of them conceptually as the average of that item. So y1 in the circle is average of item y1 across the students in the classroom. So those classroom averages, when they vary across classroom, do they exhibit variation with respect to each of these 3 factors? Do classroom really distinguish themselves with respect to all of those 3, or is it just one single aggressiveness factor in the classroom, that some classrooms are just mismanaged by teachers who can't handle the kids? So they are aggressive in all regards, not specifically some classrooms varying more on FB1 than FB3. So you can ask those kinds of questions. And Linda will have an example from achievement modeling where on the between level, the factor has more to do with the excellence of the school in that case. So maybe there's only one dimension on the between level. In any case, it's not at all clear that you will have as many factors on the between level as on the within level. Typically, you have fewer on the between level. And at the very least, the loadings could be quite different on within and between. And it's important to be able to do this factor analysis correctly. Even if you're only interested in the within structure, you want to be able to take into account the non-independence of observations by modeling the between structure, by including, allowing for across classroom variation in this case. You don't necessarily, if you're only interested in this part of the model, you don't necessarily have to have a specific factor model for between. You can have a saturated model that is allowing free correlations between all of these variables. And that can be done very easily when you have continuous outcomes. But it's much harder to do when you have categorical outcomes, because with categorical outcomes and continuous latent variables, you get into these numerical integrations with number of dimensions increasing as a function of the number of factors. And when you have many, then it gets too heavy. And it's very hard to have a saturated between model in that case. But we'll talk more about that example tomorrow in terms of this new exciting feature in the upcoming Mplus version 5. A complete brand new technique for doing two-level latent variable modeling for categorical and other non-normal outcomes. That is much, much easier to handle in terms of computing demands, where we can work with many more dimensions than we can otherwise. And that'll be part of your 5B handout. So for those of you who are going to go home this afternoon, now you have to reschedule your flight. And to make a long story short, here is, for those of you who just have to go home, here's the story. We have a way here then to do exploratory factor analysis on within and between in the correct way, taking into account categorical nature of the data. And it seems to be factor 1 here, harms others, break things, seems to be a property. Taking others property, harms property, seems to be a property aggression factor. Yells at others, stubborn, talks back to adults. Factor 2 seems to be the verbal aggressiveness. Factor 3, fights, teases classmates, fights with classmates, seem to pick up some of that person aggression factor. It's EFA style, so you have a lot of other loadings, small, which are insignificant when they are not bolded. Now on the between level, I tried to pull out 3 factors there as well, and it looks like there are actually 3 factors there. So classroom, some recent classroom seems to vary in their, with respect to all of these different factors. You can separate the factors. So it's breaking things, taking out this property, harming property comes through. There is a little bit difference though. Lies here, for instance, that loading was not that big in the within level. What about the verbal aggression? Stubborn, yells at others, yes. This loading is a little bit smaller than that, but perhaps not significantly so. Pretty much the same here. And loading, factor 3, it's the person offense, harming others, comes through more clearly here. Fighting with classmates. So there seemed to be possibly, I think your microphone is on.
It is.
I'm glad you didn't say anything secret. Seemed to be 3 factors supported on both levels, which surprises me actually. So there is variation in these 3 dimensions on both levels. Actually, I haven't seen that before in other data, but then again, I've been working with achievement data mostly, and not these behavioral data. The loading structure is not exactly the same, but it could be of interest to test lambda b equality to lambda within, just to see if it's measured the same way. In any case, usually we do want to focus on the within level factors, and be sure to, you can imagine that from this kind of analysis, you can then simplify and create a verbal aggression score by summing up the items that load on that factor, and summing up the property aggressions items into that factor, proxy for that factor, etc. for the person aggression. But since each factor has yet relatively few items, verbal aggression, 1, 2, 3, 4, there is a case that we talked about yesterday where it might be a better approach to work with 4 multiple indicators of a factor in whatever analysis you do later. And tomorrow we'll talk about a logistic regression onto the verbal aggression factor. So for instance, juvenile delinquency could be regressed on the factor of verbal aggression, or on the factor of property aggression, or on the factor of person aggression, each with several different indicators. And you can see which form of aggression in fall of first grade is most predictive of juvenile delinquency in that logistic regression. But that would be a logistic regression with latent covariates, where you've sorted out the different forms of aggressiveness. Another example that you see tomorrow is growth model, a growth model with multiple indicators, like we talked about yesterday afternoon, where the development over time is quite different across, for the person regression factor at least, relative to the other factors. And that then ties into intervention studies where the intervention influences the development over time, as we talked about yesterday afternoon. The intervention may have a stronger effect on one of the three than the others. I don't know. I haven't done that analysis yet. But there is reason to take a close look at your measurement instruments and tease out the dimensions. And to do that in multi-level settings, you have to do multi-level factor analysis. And there, I'll hand over to Linda.
I have a question for you that probably somebody else is going to ask. How did you do EFA with 2-level?
Oh, I thought they would never ask that. I was hoping.
We don't do that in Mplus.
Well, I just made it up.
Did you do EFA in the CFA framework?
No, what I did was in this new version of Mplus that we're testing out, it's possible, even with categorical outcomes, to print out an estimated sigma within and an estimated sigma between matrix from a basic analysis, right. And then you can submit that to an EFA program.
So that's what we recommend people do with continuous outcomes. Analyze the pooled within matrix and the sigma between, but we've not been able to do that before for categorical outcomes. So I guess while I was busy answering email, you were sneaking this analysis by me. Okay, so then that's a good thing, though. You'll be able to do that for categorical outcomes in the future. And always when you're building up these multi-level models, it's a good idea to start first to fit for the within part of the model, then fit the between part of the model before you put them together. And with categorical outcomes, this just hasn't been possible before. Okay. So we're going to talk now about 2-level factor analysis with covariates. And we're going to look at the model over here. And this is a situation where we have a different number of factors on within 2 than we have on between, where we have only 1. And as Bengt just showed you an example where there were the same number on both. And basically, whether they're the same number or whether they're a different number is really due to the context or due to the substantive area you're looking at and what makes sense. And as Bengt mentioned, in the education data he's usually looks at, he hasn't seen the same number of factors that often fit well. But with this aggression data, it seems to have worked out. So this is really something that you decide substantively. So you might want to think of these factors that haven't been named actually as math achievement and verbal achievement, so math and verbal factors, and just a general factor on the between level, a general achievement factor. Because with schools, it's hard to think that there would be a school where students did really well on math and didn't do very well on English. You know, that doesn't make sense for a school. Schools either do poorly overall or do well overall. So you might consider then, if the cluster was school, that factor could be a general achievement factor. So the path diagram doesn't really have anything new in it except the addition of covariates. So we have our 2 factors, and on the within level, we're regressing on 2 covariates, x1 and x2. And on the between level, we're regressing on 1 cluster level covariate, W. Let's go over here. Oh, I forgot. Okay. So let me just give you an example of what the input would look like. We're fairly familiar with this now. We're saying that x1 and x2 are within variables, so they'll be modeled only on within, and that w is a between variable, which means it was measured on as a cluster variable, only on the cluster level, and can only be analyzed on the between level. And the cluster, nothing new there. So how do we add the covariates? Well, we've defined our factors using the by statement. So and as Bengt had mentioned earlier, f1 by y1 through y3 is the same as y1 through y3 on f1. And you might wonder, well, why don't you just use the on command for that? But we needed to come up with a way to give a name to the latent variable, so we created the by command. So f1w tells us that there's a latent variable named f1w that's measured by the indicators y1 through y3. And that same thing comes up with all of the bar commands where we put a name on the left-hand side. So all latent variables are named within the model command. All observed variables are named in the variable command. So when you see beta 1 bar, that's just a convention for giving a name to what's happening on the right-hand side of the bar. So here we have named the factors F1, FW1, FW2, and then we want to regress those factors on a set of covariates, and we use the on option for that. So F1 regressed on X1 and X2, and F2 regressed on X1 and X2. We could have also said F1, FW1, FW2 on X1, X2. And on the between level, we just define the factor FB by putting FB on the left-hand side of by, and then we do the by statement, FB by Y1 through Y6, and regress FB on W, as shown in the path diagram. So it's pretty easy to translate, I think, from path diagrams into the Mplus language if you understand that by is measured by, on is regressed on, and with is correlated or covaried with. Now that's what the input would be like to analyze that. Now I'm going to show you a Monte Carlo input that was used to generate data for this. And talk a little bit. We never used to bring in any Monte Carlo inputs, and people always wanted to know more about it, so we're trying to do that a little bit more. And I wanted to talk to you about, in particular, generating the two-level data and the special parts of the Monte Carlo command that are used for that. So Monte Carlo : that's a special command that's just for Monte Carlo simulation studies. And we have many options that are the same options used in other paragraphs or other commands. For example, names are, we also find in the variable command to name the variables. And you're doing the same thing here. You're giving the names of the variables you're going to generate. So you're saying, I'm going to generate Y1 through Y6, X1, X2, and W. And you're going to generate those variables, and then you're going to refer to them by that name in the model command when you analyze them. You have your number of observations, 1,000. And then related to clustering, we have NC sizes and C sizes. NC sizes options tells you how many different sizes of clusters you're going to have. So we're going to have 3 different cluster sizes. And C sizes tells you how many clusters of each size are you going to generate. So this says we're going to generate 40 clusters of size 5, 50 clusters of size 10, and 20 clusters of size 15. And reps, we're just doing 1. You can just do 1 rep if you just want to generate a data set. And we're saving it. We're saying that X1 and X2 are going to be within variables, and W is going to be a between variable. Okay, so then the next part of this is there are 2 model commands that you need to use when you're doing a Monte Carlo simulation study. You have to use model population. Model population gives the values that are used for data generation. So it gives the population values for data generation. You have to give a value for every parameter in the model. If you do not give a value for a parameter, the value 0 is used, and that's usually not going to help your simulation results. So, and you can use either the @ or the asterisk to give the values, because the only thing that's happening with model population is it's being parsed and the values are being taken as the population values for data generation. So right here we're saying we refer to variances of variables by just referring to the variable names. So the variances of x1 and x2 are going to be 1. The factor loadings for F1, FW1 for y1 is going to be 1. Y2 through y3 are also going to be 1. So we're and then let's just take another one here. The variances for factor 1 on x1, the population value for that regression coefficient will be 0.5. For x2, the regression coefficient population value will be 0.7. So model population just gives the values to use for generating data. Now the model command that you give is what is used for data analysis. So you have to keep, when you're doing a simulation study, you have to keep track, generating the data, analyzing the data. So there are options for data generation, and there are options for data analysis. So the plain model command is the analysis model. And the values that are given here are used both for starting values and for coverage. Like, remember Banks showed you the 95% coverage column was the second to last column in the Monte Carlo output. These values are used for coverage. So if you're generating data that have a population value of 0.5, you want to compare that to the population value of 0.5 in the coverage column. But we have them in different places for flexibility, because sometimes you may want to analyze the data differently than the way you generated it. So your question that you're trying to answer with your Monte Carlo simulation study might have to do with the fact that if I generate data as categorical, for example, and I analyze it as continuous, how far off are my parameter estimates? You know, is this really going to hurt me? And that's why I say when people ask questions about, well, what size of a sample do I need for this problem, or what's going to happen in this situation, how much power do I have? The only way to really tell is to do a simulation study and to generate data like the data you have and then analyze it the way that you think is appropriate and see if you get the right results. And you can do that in Mplus. If not through regular Monte Carlo, we have an external Monte Carlo facility where you can generate the data within the regular Monte Carlo, save it, and then analyze it through the external Monte Carlo. So, go ahead.
Which is located in Chicago, right?
No, I don't think so. All right, so that's more about Monte Carlo and how that can be used. All right, so then let's go on to another example. Oh, no, we're not doing that one. I forgot. Let me see. Yeah, so just enjoy that while I find the page that we're going to. No, we're not doing longitudinal. Okay, so slide 107. Actually, I'm going to do 108 here and 107 over here. Nope. Oh, it'll come. All right, so now we're going to be looking at the Nels data again. We already looked at that earlier. But in this analysis, we're going to look at 4 variables: reading, math, science, and history, citizenship, geography, which I'm going to call history, and a set of background variables. And we're going to be looking at a multiple group analysis. two-level. So we have not only between and within, but multiple groups. The groups are public schools and Catholic schools. So this is I think somebody's asked about this multiple group, multi-level modeling, and we can do that in Mplus. So we're looking at a pretty complex model here. The path diagram is an old one, so it's not drawn exactly like you're used to seeing, so I'll point out those differences as I explain it. One thing is we have between on the top and within on the bottom. So let's look at the within part of the model first. And we have only the observed variables shown here, y1 through y5, 6 through 9, etc. We don't show their counterparts in circles on the between level. So in a newer diagram, we would have circles for each of these that the within factors would be pointing to. So what do we have here? Well, on the within level, we have a general factor, specific factor model. So this is something that you would have seen in our traditional modeling day one, this type of a model. So in this type of a model, all of the items load on a general factor, and then certain items load on the specific factors. So we have one general factor pointing to every item, and then a math, a science, and a history, three factors, math, science, and history, pointing to specific factor indicators that are related to those topic areas. And then we have a regression of all of these factors, general and specific, on SES and on gender. So it's a more complex model than we've looked at, but the idea is the same. Now, this is a situation where we felt there might be one specific factor on between and the general factor. So we have fewer factors on between, but still not just one general factor. But as on within, the general factor points to all of the items, but the random intercept of all the items. And then the specific factor points to certain other items. And you'll note that they're the same as the math items on the within level. And then we regress those factors onto between level covariates, SES and minority. So let's, on this screen, take a look at how we would set that up. So we haven't talked about the grouping option before. That's something new for this session of courses. So when you do multiple group analysis for most models, you would use the grouping option. And what the grouping option does is it names the variable that's the grouping variable. So that's the variable in the data set that distinguishes who's in group 1 and who's in group 2, for example. So, and then we label these groups because we need to refer to these groups in the model command, in group-specific model commands. So they have to have a name. So we say here that for the variable group, values of 1, we're going to label them public, and values of 2, we're going to label Catholic. So our grouping variable is school type, public versus Catholic. And we have our normal cluster variables. Cluster variable is cluster. We are saying gender is a within variable, and minority is a between variable. So all the other variables that we've mentioned here as covariates are going to be modeled on both within and between. So we have our analysis. We say type equals 2 level. That's all we have to say here. We could say missing, which will be the default in version 5. But what's most important, and actually I should probably have the picture of the model to discuss this, is how we specify the model in the model command. There. So here's the picture. So in the within part of the model, we use the by option to define the 4 factors. General W, by, and then we give all of the factor indicators. And you'll note that we've used a hyphen here, the list option, so Y8 through Y16 is going to include all the variables on either the names or use observations list that encompass Y6 to Y16. You'll note one other feature in this input that you haven't seen before, and you see the asterisk, which means we're freeing the factor loading for Y1. Well, to set the metric of the factors, when we're defining a factor, the default is to fix the first factor loading to 1. And you can relax that default and fix another factor loading to 1, as we've done here. Or you can relax that and fix the factor variance to 1, which is just a different parameterization, but also achieves setting the metric of the factor, which you have to do for identification purposes. And then I define the 3 other specific factors, MathW, SCW, and HCGW. And you can see in all cases, except SCW, we've given a different factor indicator to set the metric. And the reason we might have done this, and something you might run into in your own work, is that we, without thinking, of course, Mplus just sets the first factor loading to 1. Well, if that factor loading, if estimated, were actually a -1, it would make convergence very difficult. And a hint, if you're doing a factor model and you're having convergence problems, you can free all the first factor loadings by putting an asterisk after them like that. And then you can fix all the factor variances to 1 by saying, for example, general W at 1. And then a lot of times that will allow you to get by the convergence problem. And if you then want to actually fix a factor loading to 1 to set the metric of the factor, you can at least see how they're all estimated and find one that looks like it's being estimated close to 1 and use it to set the metric. Because I've never seen a case where that problem doesn't point to the fact that the first factor loading is negative. So that's probably what happened here. And you'll note that we're using the width option here to fix the covariance, or I guess these are residual covariances now because we're regressing them on covariates, among the general and specific factors all at 0. Because in a model that has a general and specific factors, those parameters won't be identified. So we fix them to 0. And then we simply use the on option to regress the 4 factors, general W, etc., on gender and SES. Now on the between level, we do the same thing and we define the 2 factors, same logic. But note that we fix the residual variances of Y1 through Y16 at 0. And we do that because, for 2 reasons. One, this is normally done in most multi-level programs, and I think all that I know of other than Mplus. Those residual variances are not estimated. They're usually fixed to 0. And there's a logic behind this because they're usually very small. So we're doing that just as a convention in multi-level modeling. But one advantage in Mplus is you can estimate them. And if they're not 0, then you'll know that. And then once again, we're fixing the covariance, the residual covariance between the 2 factors at 0 and regressing the factors on SES and minority. So it's a complicated model, but I think translating it into the Mplus language is fairly straightforward. And just basically showing you a little bit of the output. So we say group public here. So public school has 195 clusters. And the group Catholic has 40 clusters. So there's a lot more public schools than Catholic schools. Average cluster size 26 for the Catholic schools, and I think that was shown here, 21 for the public schools. Now, if we look at the test of model fit, you can see that we're using the MLR estimator, although it said ML on our input. Okay, so we're using the MLR estimator because we get a scaling correction factor, which is actually less than 1. Interesting. But chi-square does not indicate good fit. The CFI and TFI, I would say, are fairly marginal. So this might not really be that well-fitting of a model.
It's a large sample.
And it's your fault. Of course. That's why we've been happily married 26 years. He figured that out.
Men are always wrong.
Exactly. No, that's not true, but. Okay, well, this thing is sleeping. Come on. Okay, so I put the results for the within part of the model, Catholic on one screen and public on the other. And what we're probably most interested in looking at is the third column here, to see which of the covariates are significant. And we can see that for the Catholic schools on the within level,
You're in the wrong column.
oh, I'm in the wrong column. No wonder nothing was significant. So anyway, we have, for the general factor, gender and SES are both significant. Gender has a negative effect, and I would imagine males are 1, so females do less well on the general factor. And for math, the situation is that gender is positive, meaning males do better on the males do better on the math W factor, also on science, and also on history. And SES is significant for the general factor, but not for the others. So that as SES increases, the scores on the general factor increase. So help me remember that now when I go over here to look at the public schools.
Gender as unknown, so we don't have to bias it.
Well, that's true. We could do that. Whoops, that's not right. So I'm going to put Catholic here. No, I don't. I'm going to put public here. So if we look at the public school, I think you see a fairly well, let's see, here's, no.
Math is different.
You have to help me on that.
Math on SES is different.
So math on SES is different. And what else is different? Let me look at this. It's hard to see.
In terms of significance, nothing else.
Okay, nothing else. So math on SES is different for public. So as SES increases, right, the math score increases. So like we saw this morning, it would appear public schools have a harder time controlling for SES within the schools. I mean, there's a bigger impact of SES in the public schools than in the Catholic schools. So it's interesting that even though these aren't real analyses from the point of view that they're going to be published, we still see similar things. And this is the NELS data. Was that the LSA data or the NELS that we looked at this morning?
NELS.
Okay. And so then we have the between results for public school, and we can take this, look at the same sort of thing. We have significant, 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 not, not. I can remember that much to get over here. Oops. It went to the beginning.
118.
Okay, and then
You want between there, so maybe it's
oh yeah, I'm on the
120.
okay. Catholic between, right? And then it looks like minority is different. Is that true? Minority is significant for Catholic, but not for public. And minority has a negative, well, it's over here that it's significant, but it has a negative effect probably. Yes? So you can interpret that, Bing, too.
We'll leave that to the audience to draw their own conclusions.
Okay. Fair enough. So anyway, but the point being, you can do multiple group, multi-level analysis of a very complex model and survive it, and also get some interesting results. And if that's something that you need to do, it's not hard to do in Mplus. Before, we could only do that with the MUML estimator, the one that's a pseudo-estimator with unbalanced data. But now, in Mplus, we can do that with maximum likelihood. And I don't have anything more to say on that. Do you? Be my guest. Oh, take this to the other podium.
Oh, thank you. So this analysis is actually from, where is it? It's not shown here. Well, actually, this analysis that Linda talked about is from an unpublished paper that was done by me and Sigtun Koo and Jan-Erik Gustafsson some 10 years ago, and we sent it to Sociological Methods and Research, and they said it was interesting, but they needed all these revisions. And we got busy with other things, so it's still an unpublished paper. So you can do that analysis and get it published somewhere now. We just wanted to open up that possibility for you. But I'm still fascinated by the fact that now when Nick is here, if you go back to this picture, Linda pointed out that you do have typically many more factors of variation on the person level, than on the cluster level, on the school level in this case. I was impressed that this analysis actually could pull out a math-specific factor, because that implies that there are some school differences with respect to their math success. So schools are not just different in terms of one factor, the general factor, which is sort of the excellence of the school, the average achievement across all subjects, across all students in the school. But there are some schools that perform a little bit better on math than others. So they have a specific target on math education, I guess. And that then can be generalized. If you think back then to the aggression case, the aggressiveness items, where we thought we had three factors: verbal aggression, person, and property aggression. We seem to find three factors on the between level as well, which surprised me for this reason. And it really means then, since those factors on the between level, those three factors are not tremendously highly correlated, it means that some classrooms will be high on, say, the verbal aggression dimension, while more average on the property and personal offense aggression dimensions, and vice versa. So classroom can differ in their aggression profile with respect to different dimensions. And I wouldn't have guessed that. So, and I don't know quite the reasons behind that, but Nick Alongo will now come up on the podium and give a lecture on that. So, but in any case, you have to think about what these factors mean. The individual level factors have a totally different meaning than the school level or cluster level factors. And again, you don't have to, if you're interested only in the within factors, you don't have to chase after the between factors. They're a little harder. We have less experience finding them. They're a little harder to do. And you could just have a totally saturated model, which is my way of saying that you impose no structure. All variables are freely correlated. And that used to be hard to do for categorical items, but it's now doable. One other angle that you might think about, because you may have much richer, more interesting data than we have access to. We sort of have to, beg and borrow data from others. So that is that when you do this factor analysis, the variables do not have to be student variables. All of these are student variables observed for the students that are then characterized in terms of their variation across students and across clusters. You could have cluster variables. you could have cluster variables combined with student variables. And the cluster variables could also be measures, could also be indicators of the between level factors, along with the within level variation part of the student level items. So that's possible. You can blend the between and within level variables and let them both indicate between level factors. And we have an example of that maybe in Paul's research. We'll see. Just a couple of thoughts on that presentation. Some of this kind of analysis is described in Joop Hox's book. Joop is active in Utrecht, the Netherlands. Here is some statistical background. And here is the background for how I got interested in this topic. This is a paper I recommend. We'll refer to that in a moment when we talk about analysis strategies. All of these papers that have Monte as authors are on our website. So now here are just some quick, what we do in the afternoons is quick overviews of other possibilities without going into details, just planting little ideas in your head. And we talked about the fact that we saw factor analysis as a random intercept model, but we can do random slopes. You could have a situation where you have these filled circles not only on the boxes signifying random intercept, but also on the arrows signifying random loadings. The loadings, factor loadings, can vary in size. They are slopes, right? They could vary in their values across the clusters as well. It's just that we will have so darn many of them. And when we have many random slopes, generally speaking, it leads to a difficult computational activity. But there is one situation that is feasible, and that's when the random slope sits on the structural coefficient here. So a dependent variable factor F2 regressed on an independent factor F1, each with multiple indicators. The structural regression coefficient, beta, can have a subscript j, or s as we call it here. So then you have this situation. You have the factor analysis between part here for the endogenous and for the exogenous factor. But then in addition, you have an s sitting here, a random slope, which is analyzed together with the other variables on the between level. Could be correlated with the other variables in some ways. And then you can have a covariate predicting that s variable. So this, I haven't seen this applied in any interesting applications, but it is feasible to do. And if you have an interesting application, whenever you have an interesting application, send them to us, and we'll loan them and put them in, or steal them, and put them into our next presentation to entertain the next group. Anyway, it's nothing special here. It's here is the random structural slope. The factor, the dependent variable factor, regressed on the independent variable factor with a random slope. That's specified on the within, and then on between you can have estimate the variation, a mean and regression of S on the cluster level covariate. So nothing really fantastically new. And this page, however, is more of general interest. That's me. And early on, when I started taking interest in multi-level factor analysis, I was inspired by Rod MacDonald and Harvey Goldstein. And Rod MacDonald had some psychometric society presentations, and he was great. He was great in always giving a handout with very detailed technical formulas. So I was working through those, and I noticed that you could do multi-level modeling as a two-group approach. Without changing software, you could do multi-level factor analysis. If you treated it as a two-group analysis, part of the analysis was a within group covariance structure, and part of the analysis is a within plus between group analysis. In any case, it led to a simple estimator, which we called MUML, just for fun, but it caught on. Mathieu's ML method. As Linda said, if you have the same number of people within clusters, it's actually ML. But typically, we don't have the same number of people within the different clusters. And then it's no longer ML, but it's still a consistent estimator. And it turns out to be a very good estimator in the sense that even for unbalanced data, unequal cluster sizes, does it give results very close to ML. So some people who developed ML for two-level analysis were disappointed that they didn't get that much different results, not even in the standard errors or chi-square. But nowadays, we do have a full information maximum likelihood estimator, full information maximum likelihood. And it has the advantage that not only do we handle random intercepts, which was the only thing we could do up here, but it also handles random slopes, if you want to. And that's useful. It is full information then for both balanced and unbalanced data. And you can do a robustification against non-normality. And more importantly, probably, it handles MAR, missing data. So missing data is handled in the best possible way. Because as soon as you're into the ML framework, as opposed to this quasi ad hoc estimator, you can handle missing data in an optimal fashion. And that's been further developed by Tirmer Asparho into more general models for non-normal outcomes as well. Model test of fit is very analogous to the single-level factor analysis case. But that's only for random intercepts models. When we have random slopes, just like we talked about before, with random slopes, there is no chi-square test model fit because there isn't the unrestricted H1 model corresponding to a mean and covariance structure. It has to do with the fact that the sufficient statistics are no longer sample means and sample variances and covariances, but the raw data. And this is the reason why in programs like HLM and MLWin, you never see an overall test of model fit, chi-square test. But we do provide it when we can in the random intercepts models, but not in the random slopes models. Model modification is available in the FIML setting as well. Model identification is just the same as for confirmatory factor analysis if you look at the within and between parts one at a time. Now, a couple of words about the size of interclass correlations. If they're small, they can be ignored. If they're small, you can ignore the fact that you have cluster sampling. You can ignore the fact that you could, in principle, have non-independent observations. But important information about between-level variability may be missed, nevertheless, if you do the conventional analysis that ignores the clustering. So it's not so much a question of how much you do wrong, how much of an error you make by ignoring clustering. It's more a question about how much you don't learn. You could still learn something about your variations between and within, even for small interclass correlations. But it is good to know what the size of the interclass correlation is, I think. And the importance of the size of an interclass correlation depends on the size of the clusters. We concluded that from the DEF reasoning, right? When you have many people per cluster, it's worse to ignore the cluster sampling and act as if you have simple random sampling. Intraclass correlations, we should remember, are attenuated by individual level measurement error. If you have a variable that has a high degree of measurement error, that measurement error creeps into the denominator, the within variation of the ICC ratio. And therefore, you can get small interclass correlations due to unreliability. But when you do latent variable modeling, of course, you disattenuate for unreliability. And therefore, it could be important to do two-level modeling, even though interclass correlations are small, when you have measurement error. And another thing to think about is that effects of clustering is not always seen in interclass correlations. Interclass correlations are more directly tied to random intercept variation, less so to random slope variation. So if you have a lot of random slope variation but small random intercept variation, you could get small intra-class correlations, but nevertheless you might want to do two-level modeling. Don't ask me to say that twice. But here's a summary then. Variables measured on the individual level can be used in both the between parts. So I guess we should, this is a great statement to have earlier. Yeah, here it comes. Sample size, all of that we've already said. Here are the steps that you may want to take, at least for continuous outcomes, and in version 5 you can actually go through them for categorical outcomes as well, using this new approach that we keep alluding to. This draws on this paper, and if you're new to two-level modeling with latent variables, particularly two-level factor analysis or two-level SEM, you may want to start with this paper. So we suggest that as a first step, you should just ignore the clustering. Just do a standard SEM model using the standard sample covariance matrix from the total sample, just to get your modeling into the right ballpark, roughly speaking. Then you start worrying about the details. You can estimate the SEM modeling using the pool within sample covariance matrix. That's S pool within. You know how you can pool within? You subtract the cluster mean, sample mean for each cluster unit. And you just do a regular SEM analysis with that as your sample covariance matrix. And it's frightfully similar in results to doing the full-fledged two-level modeling. So that's a great simple way of doing it. You just have to say that your sample size is n, the total sample minus the number of clusters. That's the right way of doing it. Technically, for those who are interested, the pool within sample covariance matrix still has a Wishart distribution. That's why the maximum likely fitting function is still correct for that. Now, that's talking about the within part, but the between part then is governed by the intra-class correlations. You know, that's the denominator is, or the numerator rather, is the between variation. So you want to know about that. And you may want to also explore the between structure using the estimated between covariance matrix, which draws on a sample of the number of clusters. And that's a little tricky sometimes because very often the sample size here is small, the number of clusters is small. And also that estimated covariance matrix may not be, and here we use that dreaded word again, may not be positive definite. That means that typically if you turn it into correlation matrix, some correlations may be greater than 1, but it may be much more subtle than that. All variances may be positive, correlations may be less than 1, but it's still not positive definite. And many of the analysis techniques we use assume that the covariance matrix is positive definite. But you can always do at least an exploratory factor analysis, at least using the unweighted least squares estimator. ULS EFA can handle any kind of non-positive definite matrix, including that one for the estimated between. So you can get a notion of how many factors you have in between. Then when you've gone through that, you know how many factors you have within, how many factors you have in between. You put it all together and do the two-level model. You know, which is a complex model, so you really benefit from taking these steps. You always build up from a less complex model to a much more complex model. So that seems to work pretty well. Now, it's 2:30, and it seems a little too heavy to get into technical aspects here, numerical integration. But there's some nice graphics here, at least. Which page am I supposed to go to?
Well, you were going to do the technical aspects. I think we were debating about that. I could do the multivariate approach.
I think we should start there, yeah.
Okay. Okay. So we've been promising you this multivariate modeling of family members all day. So now we're going to get to it. So basically, the idea of this type of modeling is that instead of having cluster equals family in your analysis and having a cluster variable that represents family, you take a univariate approach. And you allow family members to a multivariate approach, the way that we did in growth modeling, where the variables vary, y1, y2, y3, y4, we have a wide format. Well, the way you do it with family members, and this is good when you have like husband, wife, twin modeling, a couple of people. It's not good when you get probably beyond, what would you say, 4, 6? So if you go beyond 6, let's say, it becomes a little cumbersome because you have the variables on one record or several records that represent one observation for everyone within the family. So this is very useful because when you have just a husband and a wife, let's say, they are not assumed to be statistically the same. The way Bengt mentioned is done within a cluster. So within a cluster, everybody is assumed to be statistically the same. They can't have any parameter estimated differently for them. Now, when you have the multivariate approach, there are a lot more parameters available in the model estimation to model. So let's see, what do we say? We say multi-level modeling, we have independent clusters for between and within cluster variation, and we assume, as I just said, that the clusters members are statistically equivalent. And with the multivariate approaches, the clusters are independent, but we don't have to assume the statistical equivalence. And as I also said, which is on here, it's like we do with the growth model. And if you have missing data, for example, or you have a different number of people, for example, maybe you have siblings and there are 3 in one family and 2 in another and 4 in another, well, you can represent the different number of siblings by missing data. And so let's take a look at how that looks. So on this screen, we have a very, very old path diagram, which we really do need to redraw. So let me help you orient yourself in looking at this. On the top here, this is longitudinal growth model of heavy drinking for families with 2 siblings. So on the top, we're looking at the older sibling. And on the bottom, so O18 through O19 through O32, so this is the growth part of the model. At the bottom, Y18 through Y32 for the younger siblings. So we have older sibling, younger sibling. In the middle here, we are showing a growth model with a intercept growth factor for the older sibling, a linear slope growth factor for the older siblings, and a quadratic slope factor for the older sibling. And the 3 circles below here are the same growth model for the younger siblings. So here's one multivariate part of the model, and that's growth. So we have a growth model for both siblings. And what else do we have? We have covariates for the older siblings and for the younger siblings. So their gender, their high school dropout status, and what's ES?
Early start of regular drinking.
Okay, early start of regular drinking. So we can have different variables for each sibling. So that's unique. You can't do that in the univariate approach, or where we have clusters that we're not modeling. So in this, remember that whenever we have a multivariate approach, we're modeling the lack of independence rather than explicitly defining a cluster variable. It's taken care of in the modeling. But we also can have family variables. So Black, Hispanic, and these 3 are family history variables, so related to alcoholism. So let me just show you how you would set this up. So the advantage is that you can get at more parameters for the siblings than you would be able to in the other approach. So, as I've alluded to, this is actually doubly multivariate. We have repeated measures of the growth process, And then we have the siblings in a multivariate format where we're stringing them out multivariate. So that's already a 2-level model. In addition, in Mplus, you could actually do, with type equals 2 level, a 4-level model. So if we had students within schools over time that are siblings, then that would be a 4-level model. So that's another way of increasing the number of levels in the modeling in Mplus. So I guess you have families within geographical segments. Or we could have families within geographical segments over time, over family. So, and I'm going to show you how you would set this up. So the trick is that each pair of siblings is one observation. So all of their variables are in the wide format. So in the name statement of the variable command, where we describe the variables in the data set, we have the variables for the older siblings in the growth part of the model, O18 through O32. We have the variables for the younger siblings. We have the older sibling covariates, O male, OES, O high school dropout. Then we have the same variables for the younger siblings, Y male, etc. And then we have the family variables, Black, Hispanic, and the 3 family history variables. So by doing that, you consider this to be a single observation, and you can actually estimate all the 2 growth models, which we specify in the model command. We have 3, on the left-hand side of the bar, if you have 3 growth factors, then that's assumed to be an intercept, a linear slope, and a quadratic slope. Growth factors, you know, the names for 3 of them. So what we do is we create the quadratic time scores by simply multiplying the time scores that you give. And then so we specify the growth model for the older sibling, growth model for the younger sibling here. And then we regress the older sibling growth factors on both the older sibling covariates and the family covariates, and the same for the younger sibling, on the younger sibling covariates and the family covariates. And we can regress the growth factors on each other, as we've seen. So this is, if you have this type of analysis, if you have spouses or siblings or twins, it can be a very powerful way to look at it, which I don't think a lot of people do. There's a paper cited here that has done this analysis that you can look at. Ku and Mute in 2000. I thought that was a lot longer ago than 2000. Anyway, do we have that one on our website or on your website?
I think it's on the UCLA website.
Right. So we have many, many papers on our website that are available in PDF form. And a lot of Banks' papers that aren't available on our website in PDF form are available on his UCLA website, which you can link from our website when you go to the part that talks about us. And you can just click on that and take you over. So I think pretty much everything is available by PDF on one or both of those websites at this point in time. Let's see, am I going to wait for this one? No. So I think that. And then we have the twin model, which uses the same idea. You have twin 1 and twin 2, and you have that information as part of one observation. So that's the same approach that twin modeling takes, this multivariate approach. We don't really show much more here than just the path diagram. Should we take questions?
1 second. One point about slide 151 is so in this case, like Linda said, you have a univariate outcome variable, but you have a univariate for each of the 2 twins, so you have 2 columns in your data, 2 y variables. So here you do the joint analysis. it's really a multi-level model, two-level model. I don't think I've seen twin modelers do it as multi-level, but you could in principle do that. There might be some advantages to it. I just want to point out that twin and family modeling, Mplus has made a special effort in the last couple of years to improve on the possibilities of doing such modeling in a convenient fashion. And actually, I think the model constraint feature stemmed from that. And there are several interesting options related to this. When it comes to parameter constraints, for instance, you can even have constraints that are a function of observed variables. So for those who are interested in behavior genetic analysis, you may have heard of QTL analysis, quantitative trait locus analysis. And that's a case where the correlation between factors, genetic factors, vary across the pairs that you're looking at, individuals who are genetically related to different degrees. So a previous genetic analysis can give you the degree of genetic relatedness through the IBD proportions, the so-called pi hats. You can read that in as an observed variable, and the correlations between the genetic factors is moderated by that observed variable, which is an interesting general modeling idea where you have a model parameter that can vary as a function of an observed variable across individuals. And we haven't seen that in other, I don't think I've seen any other application of that, but in the genetic case. So on our website, we have several examples of genetic analysis. Michael Neal is a great statistician, has come up with his MX program that specializes in those things for the more technically inclined analyst. And they have a European website, Genome Twin website, where we started to translate several of the MX scripts into Mplus, and that's on our website. And we have some references under in papers in that left margin, under papers, and under the topic genetic analysis, you have several such papers where the behavior genetics analysts right now seem to be very interested in gene-environment interaction modeling, and there's a recent paper sitting on the website there. And most of these papers sitting on the website also then have Mplus scripts to offer. Not all of them are yet on the website, but you can email the author contact that's given there, and you will be able to get the Mplus input scripts for those. This example shows, by the way, genetic modeling where the genetic factors, the ACE factors, are explicit in the model, but in the user's guide, you have a follow-up version of this example where instead of introducing 6 factors, you introduce no factor, but instead tell the program what kind of covariance structure you have. This gives a very specific covariance structure for these 2 variables, a specific variance or covariance restriction. And when you analyze monozygotic and dizygotic twins, and it can be very easily given by a parameter restriction in model constraint, much easier than setting this up. So we are showing that in the user's guide. And as an aside to those who are BGA people, behavior genetics analysts, in the new version of Mplus coming up, we have a change of, you can actually specifically say that you don't want to have the usual Mplus default of correlated exogenous factors, but any factor can be said to have 0 covariances with any other factor without have to explicitly go in and say that for every pair. And that helps in this kind of analysis. It saves you several lines of input. It's many lines of input. And it's also useful in another kind of analysis that Jack McArdle and others are interested in, namely it's a kind of growth model analysis where the change across time is a variable of interest. Latent difference modeling, I think he calls it. And there, too, you have to spend many, many lines on setting factor correlations at 0, and here you do that just by one statement. So that would be helpful. And with that, I think we're ready for questions and answers and an enjoyable coffee break.
Go ahead.
I was wondering about the Monte Carlo simulations and whether you can use that as sort of a to learn out an analysis you might want to do in the future, like before you go into the data set.
It would be possible, I think, to do that if you know something about the population values of your data. So you know, just like in any kind of a power analysis, I mean, you have to have an idea of what you're going for. So if you have an idea of what the population values are, so you could generate data that would be the same as the data you are going to collect, because you know enough from theory, then you would be able to do something like that. And then you could plan and say, like, well, I'm not going to have enough power. And
I did a special adieu to Richard Devil.
oh, yes. Tell your wife happy birthday. So, yeah.
And we try to remember everybody's birthday.
Exactly.
Since we take their spouses away from them.
No, but yes, if you know enough about the population values to generate data, then you can use that as a way to see whether you're going to have enough power with your proposed number of observations that you're asking to get the money to collect. Sure.
On slide 115, look at you got like items Y6, Y7, Y8, 9, and 11. They're all items of the same construct, right? Wouldn't we expect for the interclass correlation to be approximately the same if the items truly belong represent the same construct at the between level?
Well, so should we expect the same interclass correlation for items loading on the same factor? I think in this case, the items are created as sums of dichotomous items, and some of the sums include more items than others. And when you have more items, the reliability go up. That has to do with the relationship between interclass correlation and unreliability. I would think it's that kind of an explanation, but otherwise you're right.
Okay. But otherwise it would hold, right?
Yep, I think so.
Slide 116. Can you help me understand or interpret the scaling correction factor, especially the scaling correction factor smaller than 1 or greater than 1? How would you interpret scaling correction factor greater than 1 or smaller than 1?
I was afraid you were going to ask that. I don't have a good interpretation for that. We're used to seeing scaling correction factors greater than 1 to indicate skewness of variables, for instance. I couldn't answer that. But let's see, I have a phone call here from my technician. I like that modern ringtone.
It came with the phone.
Yeah.
If you send me an email, I'll think about it a little bit further to remind me of that. Well, you
go.
You choose.
I don't want to choose.
Okay.
Slide 125. I see from this side you can see a random slope. That is the S, right? But where is the random intercept?
The random intercept is, let's see. I have a picture of this too,
Yeah.
right? I can get the picture.
Okay.
That's 123.
So just to remind ourselves where we are. So we have the random intercept sitting out here. And essentially, you can think of this as a random intercept. That is, you have the variation and covariation among the observed variable random intercepts is explained by F2B. So you couldn't in addition have a random intercept. That would be two latent variables. You can think of this as a random intercept on the factor level. And in addition, then you have the random slope. So it's a little bit more fun. That's a good question. You folks are getting a little bit too advanced at that.
Okay. I have a model I want to run, and I'm not sure how to do it. I've got kid and parent data on the same variable, let's say family function, and I want to create some sort of a latent difference score, and then use that to predict something else. What I've tried to do is sort of make an error term, and then use that to predict, but it won't converge. So I'm wondering how you would do that.
So you have two measures of family functioning,
Right.
taken by the child and the parent.
Yes, and I want to actually use the difference between them as a predictor of something else.
Right. So for instance, if you have multiple indicators for both the child and the parent, you have two latent variables, parent and child latent variable. And this is very much related to that latent difference analysis, Jack McArdle style that I talked about, that from those two latent variables you can create a third latent variable, which is defined as the difference. It's like the difference between F2 and F1 in this case, say, is you create an F3 here, which is equal to 1 times F2 minus 1 times F1. Fixed slopes to create that difference, and then that F3 will be the variable that you operate with afterwards. So F3 is identically equal to the difference between the previous two.
So you can create that using Mplus.
You just say F3 by semicolon. That defines that difference factor, and then you say F3 on F2 at 1 and F1 at minus 1 and F3 at 0, which sets the residual variance to 0, which implies that F3 is identically equal to that linear combination of F2 and F1.
Can you say it one more time about the F2
Yeah.
at 1 and the F1 at minus 1?
Right.
Okay.
All right. Yes, yeah.
I have a question on the slide 85. I was wondering why you have chosen Promax quotation as opposed to like direct complement or something. Is there a reason?
The question is, why did we use Promax and not parting in? No good reason. Just took one out of the tool bag.
And were you also able to get the factor correlation matrix for both of them as well?
Yes.
And were they similar?
I better go home and check that. I think the within-level correlations were around 0.5 for these two factors, but I got to remind myself of what the between-level correlations were. And that is, of course, very relevant to the question of are there really three different dimensions here? They were certainly not correlated to 0.9. I remember that much, but I don't remember where they were in the range from 0.5 to 0.9. Because the more highly correlated they are, the more indication is there that there is just a general mismanagement of the kids factor or aggressiveness factors of the kids. Yes.
I have a question about slide 135. How do I set that up? What's the command to do that? Tell it to, the sample size minus the total number of clusters.
Well, basically, when you have a covariance matrix as input, then in the data command, you would say file is, and you would give the name of the file that has the covariance matrix. Type equals covariance, and then n observations equals n minus g, whatever that number is, and you would put that number. And then you would be analyzing the covariance matrix.
So, like, save the covariance matrix.
Right, you would use the save data command. If you read the save data command, it tells you, I think it's sample equals, saves the pooled within, and sigma b saves the other one.
Okay.
I have a question about the figure on 147, the old one. So let's say you ran just a growth model for the sibling, the older sibling, and the growth model.
Up there, right.
And just the top part, and then one for the bottom part, you use the same covariates that you have on the left, but of course you can't specify any covariances within the factors. So you didn't take into account the covariance of the factors between the two siblings.
Right.
How would that affect the estimates of say the covariates predicting the factors and their standard errors?
So you would use all of the covariates, but you would drop, say, this part, the bottom part.
You would drop this, but you would keep the family covariates.
Right, you keep the family ones and
And
you
those and the
drop.
whole thing.
And you would drop this part?
Right, and this growth model here.
Or let's say you're just looking at the family variables.
Right.
Because they're the same across both.
Right.
So it's,
Well, so you would be regressing, but when in the two regressions, we regress the older sibling growth factors on the family variables and then the younger on them. And those are two different regressions. So what
let's say you weren't interested in how the growth factors across the older sibling and the younger sibling were related.
Right.
Let's say you weren't interested in that.
But you're interested in the impact on the regression coefficients for the covariates of eliminating that model?
Right.
Yeah, I think you're thinking about would you get the right standard errors here because this is on the family level. Right.
Right. Yeah. I guess I'm trying to understand if I wanted to explain to somebody, okay, if you have these kind of data, it would be preferable maybe to analyze them in this multivariate format. And the person says, well, how about if I just run a model for the older, one for the younger? I'm interested in the family variables,
yeah, so
see how they predict.
You could do an analysis of older and younger, but what this buys you is that you see the relationship. In this case, you say that younger kids are influenced by the older. That's a major advantage of this.
But if you weren't, per se, interested in that,
Then you could just say use V equals the older and the family variables and just do that analysis.
Or if older and younger are totally equivalent, you could do a two-level growth analysis, which is a three-level modeling that we can talk about after the break.
But you're saying that you just might not want to consider both siblings.
right. Maybe another way of saying this, let's say you kept the siblings as, you treated the siblings as groups, as opposed to paired observation.
So in this case, cluster. Because you couldn't do, well, they're not independent though. So multiple group requires independent groups.
Right, so what would be the impact on standard errors or the estimates of treating these paired data as independent groups?
That would be misestimating the standard errors.
Right. So you wouldn't want to take a multiple group approach when you have non-independence of the groups.
I think that's a statement we should make here. So when we talk about multi-group analysis, a typical example of male-female. So you have independent sample from female and independent sample from male. For instance, you could say that you have 2 time points, a measurement instrument has 2 time points. So longitudinal data, 2 time points. You cannot treat the 2 time points as 2 groups because they're not independent samples from 2 populations. They're a dependent sample from 1 population. So I think some of the similar reasoning comes in here. And actually, this paper is comparing this multivariate approach to the standard multi-level approach, where the younger and older siblings are treated as the same. So that's here. So the growth factor parameters, means, and variances can be different here and here. So not statistically equivalent. Now, the reason you don't do this in classroom research is that you typically don't have so many, you have like 20 kids per classroom. If you observe like 10 different variables here, with 20 kids in the classroom, you will get 200 variables to unwield it. Yeah, it will be hard. So this works well for a small number of cluster members.
Any other questions?
On slide 109. Do you weight this analysis or not? Seems to me this is like the results from unweighted analysis.
So this, we do not include a weight variable in this analysis, but we could.
Yes, well, that's my question. How and where?
Okay, how you would do that? In the variable command, you would use the weight option. You would say weight equals, and you would give the name of the variable that contains sampling weight information.
What if we want to use replication weights?
We currently can't use replication weights, but we probably will do that in version 5.
Actually, there is a paper forthcoming, I think in the SEM journal again, by Laura Stapleton, where she shows how to use replication weights in combination with Mplus. She has a little program set up to do that.
By Laura Stapleton?
Laura Stapleton,
yeah.
right.
What's the journal?
The SEM journal, Structural Patient Modeling Journal.
Oh, okay, thanks. Oh, and on the same page, that define, the line define, are we defining a new variable minority?
What the define command is used to either create new variables or transform existing variables. So we're just saying minority is equal to minority divided by 5. We're just rescaling the variable. So that's...
It's an attempt to bring down the variance of that variable to make it a little easier for convergence matters.
So it's like recoding into the same variable in SPM.
Right, exactly. We could have given it a new variable name, minority n equals minority divided by 5. But if you give it a new name, you have to add it to the used variables list. It's easier to just keep the same name because then you don't have to add it to the used variables list.
But it doesn't change the data set. It's just in the analysis.
Right.
Oh, it doesn't change my data set? That's my question.
No, you can save the data after that define statement has been done, but it won't, if you only say it in define and ask for no saving of data, your original data will be unaffected.
Right, it doesn't affect your original data, but if you keep the same variable name and you save the data, the variable will be affected in the saved data, but not in your original data. We don't touch your original data.
You mean to if I save it after the analysis?
Right.
Then, okay, got it. Thanks.
Under a new name, right.
Question here?
I had a question about the same slide. So gender and minority under the variable command are specified as within versus between. And I was just wondering if this SES is not specified. So is it because they're used, SES is used as both the within and between?
Yes.
Right, that's
exactly.
right. Yeah, so SES up here is created, as far as I remember, I'm not sure, but it's created as the average of the student level SES. Explicitly created that way. You could have taken the Mplus latent SES approach, which is in that Lutke Marsh paper that I showed you.
But we only have one SES. I think we leave it off the list to have it be on both levels.
Oh, is that what we're doing?
Yeah, well, I think so. I mean, it's on the names list, and we're always using the same thing on one, I think.
Well, Linda looks at that. Note that between, what?
Yeah, we use the same name, so it has to be that we're just...
Can you go to the previous slide, 109? Just a comment, minority here is a percent minority in the school, so it's a continuous variable. You probably guessed that already. All right, yes.
123. Can you relate this to your concrete scenario or some example? It's kind of difficult to follow.
Some example? Well, let's say that this is a set of achievement test scores in schools. And let's say that this indicators of socioeconomic status, income, education, etc. And you create factors, and you say that the regression of achievement factor on the SES factor has a slope that does vary across schools. You know, for the same reason as we said before, some schools are more successful at being egalitarian, equalizing pre-existing differences than other schools. That will be one example.
What is X and S?
Then S is the random slope, which you can try to explain by school level covariates here. And a school level covariate that's related to a school becoming more egalitarian, I do not know. But I'm sure there are some. I hope there are some. I wish I had a catchy marketing example for you. But you'll think of one and email it to me. I'll use it next time. There are some of these models that we haven't arrived at due to applications, but just due to we know, okay, here's a methodological modeling void, we'll fill that, and if we build it, they'll come, we figure.
All right, any more questions? One back there.
I was wondering,
and then we'll have a break.
I was just wondering on slide 82, if you had considered a polynomous IRT model for the analysis of the survey data, and if you rejected it, why?
A IRT model for survey data. Yeah. This is actually an IRT model. The way I ultimately analyze it, that's ordered categorical. It's a sum edema logistic model, and it could be. And it's two-level, so it takes into account clustering, and it could be combined with stratification and weights. So yes, you could do multi-level complex survey data IRT. You can do it currently by maximum likelihood, but in version 5 by a simpler approach as well.
Okay, well, maybe we should take a break now and come back.